All right. So hi, everyone, and welcome back to the EMS webinar series. I'm especially excited about today's event because I'm joined by someone who's been not just a brilliant scientist, but a constant source of support and inspiration in my own journey, Professor Peter Butt. So Peter is a professor of polymer chemistry at the University of Manchester, where his connection with the university actually goes way back. He earned both his bachelor degree and PhD degree in chemistry, after which he was headed to BP Research Center at Sunbury-on-Thames for several years. He returned to Manchester as a lecturer, and he's been shaping the field and many of us in it ever since. So he's a truly Mancunian professor, but actually he was born in Eritrea. And I guess today he will talk about that a little bit. So his research focuses on the design of novel polymers, including polymers of intrinsic microporosity. And he's one of the co-inventors of these fascinating materials. So beyond the CV, I've had the privilege of collaborating with Peter for over 13 years now. And I can honestly say that his mentorship, patience, and guidance have been incredibly meaningful to me, both professionally and personally. So it is my pleasure to host this podcast and his webinar today. So Peter, before we start the research webinar, I would like to go through a couple of questions and have a discussion with you about your journey. So when we were preparing for this, you mentioned that you were inspired to choose science as your profession back in the early days when you were actually in Eritrea. So can you tell me a little bit about how you started to like science and why did you choose this profession?
Yes, indeed. I think, like with many people, it was a good teacher, and you can't underestimate the value of a really good teacher. And I spent my primary school was actually in London, but then between the ages of 10 and 14, I was back in Asmara in Eritrea, which at that time was part of Ethiopia, and I was going to a very small English school in Asmara. And so we didn't have many teachers. I think there were only about 50 students altogether across all of the years. But we had one teacher who was a physicist, but she taught all of the scientists, a brilliant teacher, Christine Stone. And she really was inspiring to get me interested in all aspects of science. I remember she, in this tiny school, she managed to get funding to set up a little tiny laboratory. And but we did have an incident one time where she tried to do a chemistry experiment and the room started filling with chlorine vapor and we had to evacuate quickly. So a very early experience of the hazards of working with chemicals as well as the inspiration of doing science. When I was 14, I came back to England and I had 3 years at a boarding school, in fact, in southeast of England in Ramsgate. And again, we had some good science teachers there, and that's where I did what were then called O-levels, or some more O-levels, and A-levels before going on to university.
Okay, and how did you get into chemistry? Because initially you were interested in rather medicine than chemistry, right?
Yes, I thought that one ought to do something to help people, and I thought medicine was a good thing to do, though I think secretly I always wanted to be a scientist. And in the end, I didn't get into medicine, but I did get into chemistry and subsequently stayed in chemistry, really, although I've been collaborating with people in other disciplines. And it's been a very good career for me and something that I found interesting and exciting.
Okay, so before we talk about collaborations, when I was reading your CV, so you worked in the industry as well, right? A good number of years at BP.
That's right. I had 8 years in industry. So, well, when I was a student in the UK, an undergraduate degree was only a 3-year degree for bachelors. We didn't have 4-year degrees like we have now. And a PhD in the UK was three years, no more. So I had 6 years at university, and then I was off into industry. it was a period a bit like now when actually the job situation was quite difficult. A lot of companies weren't employing chemists in particular. So I ended up choosing between two job options, both with BP, one at Sunbury-on-Thames, which at that time was their central research centre, and one up in Grangemouth, where they had a large part of what was then a chemicals business. And I went to Sunbury, where you were able to do some interesting exploratory research as well as industrial research. So it's a little bit like a halfway house between academia and industry in many ways. So I was there for 8 years. That was in the 1980s, which was a time, people may forget this, but it was a time when people were worried that oil might run out by the end of the century. So something which is, again, very topical, there was a lot of interest in diversification, looking into things other than oil. So there's a big chemicals business, and they were getting very much into advanced materials, including membranes. So it was while I was at BP, I got particularly involved indirectly in membrane research. I was in a group that provided a service to other researchers, a polymer physics group. So amongst other things, we did polymer characterization. And we were working with one group which was developing membranes for evaporation, and another group which was developing membranes for gas separation. So I was on the periphery of membrane research even in those days, though I got more directly involved later, as I'll mention in the talk.
Okay, that's great. I wanted to ask you anyway, how did you end up working in the field of membranes, membrane science and technology? But now here we have the answer. Is there any other... Yes.
Yeah. Well, actually, at that time, I didn't know it was going to be a long-term thing. I actually decided not to join a membrane group while I was at BP because I wasn't. And of course, things then changed at the end of the 80s. So when I got an opportunity to leave and move into academia, very soon after that, the company direction changed. It was focused much more on oil and gas again. And it actually closed down the corporate research. So everything that had been going on then came to an end not too long afterwards, unfortunately. But I certainly got some introduction to membrane research. And it was after I moved to Manchester, I was actually sponsored by a different company, by Unilever initially. A lot of my interest at that time was water-soluble polymers and in particular polyelectrolyte behavior. And they wanted me to look at polyelectrolytes as structure directing agents in zeolite synthesis, which got me involved with zeolites. And a bit as an accident, we found we could make some zeolite membranes. And that really indirectly got me back into working with membranes. And then PIMS came along and it became a much bigger part of my research.
So obviously these industrial experiences significantly shaped your career and your way of thinking probably. Do you have any recommendations for young scientists? Is it a good idea if they kind of finish their PhD, postdoc, they go to industry, then go back to academia? What is your advice?
If you can do it, it's very good. It's not always easy to make that transition back. It wasn't easy when I did it. And the university system, at least in the UK, doesn't always know how to really cope with people who have a slightly different career path. And so there are positives and negatives. In terms of my teaching and my research, I think it was an incredibly valuable experience to have that industrial background. And there were a lot of things in terms of even the way I taught that were informed by the things I learned at BP. Actually, nowadays we teach a lot more about things like communication skills, but when I was doing my PhD, we had very little chance to practice, only very few presentations and things. And so when I joined BP, one of the first things they did with their new PhD students was put them on a very intensive and tough communication skills course. It was 1 week, and that was probably the most valuable week training I've had in my life because I've used that ever since.
Interesting to hear that. Yeah, myself, I also worked in the industry for a couple of years, and it also had an influence on me and on my teaching. I think that students enjoy a lot if you have industrial experience, and then you can give them case studies and examples, real life examples. So it's not only affecting our research, but also our teaching.
Exactly.
And then you mentioned diversification and gas separation, which was already a hot topic in the 80s. But nowadays, again, diversification, gas separation, looking at advanced materials, it's living its renaissance again, no?
Well, when you get to my age, you see a lot of things coming round and around and around again, both in academia and industry. So yes, there's a lot of interest in separations, in membrane separations, in trying to develop gas separation membranes in the 80s, particularly with a focus on polyimides. And so they have quite a large group at BP, as well as, of course, places elsewhere, looking at many different polyimides for gas separations.
Yes. And then, your research area, and probably you will talk about different aspects of PINs today. It covers polymer chemistry, which is your training and your background originally, but then you also work with separations, right? Separations, gas separation in particular, process development, even transport through membrane materials, advanced materials. So it is very interdisciplinary. How do you cope with that? And how do you choose your collaborations? And how do you navigate in these diverse fields?
I mean, that, as part of the fun of science is that you're always learning new things. You never know everything. And I remember a long time ago someone saying that in research, the greatest opportunities were often at the interfaces between disciplines. And I think I found that to a large extent to be true, that when people from different disciplines learn to interact and communicate and work together, that's when some big step forwards can be made. And the membrane field is very much an interdisciplinary field. A lot of people in it are chemical engineers, but if you're thinking about new materials, new membranes, you have to work with chemists and material scientists and physicists to really understand what's going on. And that's what makes it really interesting. Collaborations, I find they sort of come along. And often it's, as many people know, as I'll mention, that the story of PIM starts out with the collaboration between myself and Neil McKeown. We started out as friends and colleagues, got working together, and it led to a whole new field in a sense. And then, and I'll mention it again in the talk, but along the way, other people have been involved, international collaborations of various sorts. We couldn't have done without them. We simply, particularly in the chemistry department, we can make polymers, we can characterize them, but there's a limit to what we can do in terms of real testing and understanding the performance. And so it's been through good collaborations that we've been able to make real progress. And bringing different people's knowledge and skills together, it's invaluable.
Yes. So you mentioned good collaboration, but what makes or breaks a collaboration? So there are many collaborations, right? And some of them can be successful, others are not. And it's not always about the research itself, but it's about the personal connection.
It is very much about the personal connections. At the end of the day, scientists are people and collaborators are people, and a lot depends on finding people that you can relate to and work with, and to a certain extent, trust. If there isn't a basis of trust, then you're never going to have an effective collaboration. And so in my time, some people I've worked with, it's developed into a really good relationship. Others perhaps have fizzled out after a while. But a good collaboration is based on good personal relationships, in my experience, that the people have to get on. And then there's the excitement and the enthusiasm to make the research work.
Yes, thank you for these thoughts. And I'm just thinking about collaborations and how the scientific world has changed over the past years and decades, and everything is speeding up. So you need results quick, you need more and more collaborations, you need to publish. There is a pressure on academics. What are your thoughts on that?
My first thought is if I was starting now, I'm not sure I'd have gone into academia. The pressures there've always been pressures, there've always been difficulties. They change over time. But I do think the pressure on a young academic now to produce results quickly isn't necessarily good for them or for the subject. That people need time to bed in and to find their way. And if you're not careful, you end up with too much that is superficial in terms of research, that people haven't got the time to really dig in, get into the depths of understanding what they're doing. And all too often, people are reinventing the wheel because they haven't had the chance to really explore what has already been done, and to build on that. So I do worry that the pressure on young academics now is actually too much, and it is getting harder and harder to really make good science and really develop the subject well in that context.
Yeah, I couldn't agree more. So let's see what the future brings.
Yeah.
Okay, but before we start your presentation, maybe one final question, which is more on the personal side. So what do you like to do in your free time? What are your hobbies?
So the main thing is whenever I can to get out walking with my wife, if possible, out in, if you know England, you know we've got the Peak District close to Manchester, which is a beautiful area. And I particularly love the Lake District. In fact, I was there last week, where we've got lots of beautiful walking. You can just get out, enjoy nature, forget about all the worries of life, and just appreciate everything that's around one. That's the best thing.
Yes, I think that's great to get out of Manchester. And I used to go to Edale as well for short hikes, and it's just around the corner with the train. So it's pretty nice. All right. So shall we get down to PIMS?
Okay.
And the research and your background and how PIMS came about. So the stage is yours. You have about 40 minutes for your presentation. I will come back then, and then we're going to continue with the Q&A. Thank you for the chat, Peter.
Okay, well, this is about 21 years of PIMS. It's 21 years since the first publications, although, as I'll say, the story goes back a little bit longer than that. But it is something that I've been excited and to be involved with. It's something that I've really enjoyed. And I've already mentioned a bit about my own background, that I studied at Manchester, BSc in 1978, PhD in 1981. I then went for 8 years into industry, working for the BP Research Centre at Sunbury-on-Thames. And there's an image there with me actually with what was an early form of flow field flow fractionation, a way of separating very large macromolecules and colloids, which I think that was probably the first membrane I made myself, because I, in a very crude way, cast a cellulose acetate membrane. But I was also involved in working with other groups at the BP Research Centre involved in membrane research, and in particular evaporation membranes, hydrophilic evaporation membranes in that case, and gas separation membranes. And so I got to know a little bit about membrane science and some other people involved in the field while I was in industry. When I moved back to Manchester as an academic, I was initially sponsored along with a professor who joined at the same time by Unilever. And Unilever got me involved in work on zeolites, even though I was primarily a polymer chemist. And along the way, we found we could make some zeolite A membranes, which really love water and really good for transporting water. And we were actually looking at zeolite membranes as evaporation and vapor permeation membranes. And that involvement in membrane research with zeolite membranes, with inorganic membranes, was actually quite useful later when I got back into doing what I'm meant to do, which is polymer chemistry, and we realized we had some polymers that would be good for membrane research. A colleague and friend at Manchester was Neil McKeown. He later moved to Cardiff. He's now at Edinburgh University. But we got involved in some collaborative work where we were focused on trying to develop actually polymer networks which would be nanoporous, which would have a lot of space in them. Now, Neil was an expert in phthalocyanines, and phthalocyanines are big plate-like molecules which have a metal ion at the center, which can take part in various sorts of catalytic reactions. But phthalocyanines, these sort of flat plate-like molecules, tend to stack together. And so what we were trying to do at that time was to build phthalocyanines and similar molecules into a polymer network in such a way that the plate-like molecules were prevented from stacking. And Neil, who's a brilliant organic chemist and comes up with all sorts of bright ideas, he thought of a way of building these phthalocyanine units into a network which kept the plate-like phthalocyanine molecules separate from each other and created space that little molecules could get in. And our focus at that time was actually catalysis, trying to make these more effective as heterogeneous catalysts. And here we have an image from those days, which is an example of a cobalt phthalocyanine-based nanoporous network polymer. Now, if we do something like nitrogen absorption, desorption, liquid nitrogen temperature, what we can see is very strong absorption at very low relative pressure. This is typical of what people in the absorption field call a microporous material. In this context, microporous means that we have pores less than a couple of nanometers in dimension. And the importance of those very tiny pores, less than a couple of nanometers, is that if you have a small molecule sat in that pore, it feels the walls all around it. So even relatively weak interactions with the surrounding polymer are magnified just because of multi-wall interactions. And that's why a particular feature of these materials that's called microporous materials in this context is to get very strong absorption at very low relative pressure. And so typical examples are things like zeolites and activated carbons, and these nanoporous network polymers behave in much the same way. And there is a slight difference in that the desorption behavior is a little bit different to the adsorption behavior. That's a hysteresis, but it's not the sort of hysteresis you get when you have a material with slightly larger pores, what are called mesopores, 2 to 50 nanometers, which is where another type of absorption occurs that involves capillary condensation. And in that case, the desorption curve will always close. It'll meet the absorption curve at a relative pressure when we deal with nitrogen at 77 K, a 0.4 or above. But this hysteresis extends to low relative pressures, and that's typical of very many polymeric nanoporous materials, which can perhaps swell a bit and which also have a very complex distribution of micropores. Now, the chemistry that we used in creating these networks was some chemistry that had been worked out. Aromatic nucleophilic substitution is something that any organic chemist knows about. But Jeff Eastman, who was at Liverpool University and actually did a lot of work on polyimide membrane materials, he'd worked out for small molecules that you could get a very effective double aromatic nucleophilic substitution reaction if you have the right activated species that gave this dibenzodioxane linkage, a sort of a fused ring structure. And what Neil realized was that you could apply this to create the sorts of networks that I've just described. And we then went on to apply the same chemistry to create a non-network, a linear polymer. Now, when we originally did this, and this is the polymer that later became known as PIM1, and we also looked at a variety of others, when we first did this, we were thinking of it just as a control experiment because we were focused on network polymers. And in fact, this sat in a drawer for a while before anyone got round to measuring its properties. But then when they did the BET analysis, we realized that we actually had something quite interesting. I'll just go ahead. We actually had something that behaved like a microporous material, even though this wasn't a network polymer, it was a linear polymer. And we've been thinking that you had to have a network to get this sort of behavior, but no, you didn't. You just need to have the sorts of features that we have in PIM1. What we've done with this structure, which is all fused rings. There's no single bonds in the backbone. So there's much less conformational flexibility than in a conventional polymer. But by having a spirocenter in the polymer, if we just look at it, here's a little bit of a structure of the polymer. The spirocenter is where we have two 5-membered rings, in this case, connected by a single carbon atom, a tetrahedral carbon atom, and so that puts a bend in the chain. And if we have a lot of these bends, we end up with a polymer that twists and turns a bit like a normal polymer, but because of the fused ring structure, it can't change its conformation in the same way. So these spirocenters, which are examples of what we call sites of contortion, they put bends in the backbone, but now we have something which can't pack effectively, and we end up with high free volume. We end up with something which is like a microporous material in the sense in which I've described it, even though it's a linear polymer, and even though, because it's linear polymer, unlike a network, unlike a zeolite, unlike an activated carbon or any of these other microporous materials, it can be dissolved in certain solvents. Solvents, not necessarily the nicest solvents, but solvents like chloroform and tetrahydrofuran. And therefore, it can be processed from solution. So we had something which we could coat, we could turn it into a film, we could make fibers from it, and yet in the solid state, it behaved like a microporous material. It behaved in many ways like an activated carbon. So this was something really quite interesting that we tried to develop, and at an early stage realized that it would have applications in the membrane field. So the basic concept, this led to the basic concept of a polymer of intrinsic microporosity, or PIM. If we think about a normal flexible polymer, the chains can rearrange, wiggle around, and more or less fill space. And of course, we can make very rigid polymers that are quite, if you like, straight and stretched out, but they tend to stack together and be very difficult to dissolve or do anything with. But if we have this polymer backbone with a combination of features, the sites of contortion that makes it twist and turn, but also the lack of conformational flexibility, then we end up with something which traps a lot of free volume. It traps a lot of space that other little molecules can get into. And that's the basic concept of a PIM. Well, we thought this might be quite interesting, so we filed a British patent, and the application went in 2003. In fact, the application went in the day before a conference when Neil did say a little bit about these polymers, a conference up in Edinburgh. But the first publications came out in 2004, where there was a chemical communication on the concept of what, by this stage, we were calling a polymer of intrinsic microporosity. We spent quite a while worrying about what to call these polymers. And also the first membrane application. And because I'd been looking at zeolite membranes for hydrophilic pervaporation, the obvious thing for us to look at quickly was membranes, but in this case, we have a polymer which is hydrophobic, and we were looking at organophilic evaporation. In fact, we were looking at removing phenol from aqueous media. So 2004 were the first communications on solution processable polymers of intrinsic microporosity that could be readily processed from solution into membranes of one form or another. Well, we thought right from the start that if we could make membranes, and that they might be interested in gas separation, but we didn't have the kit. I did actually try to get some money out of the Research Council to build some gas separation kit, and they didn't give me the money. So this is one case where we had to really collaborate in order to make progress. And I'd met Detlef Fritsch. Now, he was at the Helmholtz-Zentrum in Gestalt, which at that time was called GKSS. And GKSS at that time, they had a lot of people working on all aspects of membranes. And I'm sure many of you are aware of that. But we got involved, collaborated with Detlef. That enabled us to get some data for gas separation. And we looked at initially at two PIMs, PIM 1, which I've mentioned, and also another PIM, which we call PIM 7. And the interesting thing is that we found that we did have polymers which were much more permeable than most polymers, perhaps not quite as permeable as polymethyl-propyne, but more permeable than most polymers, whilst being relatively selective. And those of you involved with membranes for gas separations will probably be well familiar with the Robeson plots. Robeson, back in 1991, collected together all of the data that were then available for polymers for gas separations. And he plotted for a variety of gas pairs on double logarithmic scales, selectivity against permeability, and simply drew a line through the best performing points. And that represented in 1991 the limits of performance with polymeric membranes for those particular gas pairs. And the example we have here is the oxygen-nitrogen gas pair. There are a number of others. And what we see is that PIM1 and PIM7 broke that upper bound, that we not only had a relatively permeable polymer, but that it was more selective than had thought to be generally feasible at the time. Well, a few other polymers came out. So in 2008, Robeson went back to the data and he proposed new upper bounds. So this is the thing with, as chemists, we're always trying to develop new materials and try to outperform what's been there before, but then the goalposts move. And so PIM1 and PIM7, along with a few other polymers which had been developed at the time, were used to define the new upper bounds in 2008 for a number of gas pairs. And also in 2008, Robeson introduced an upper bound for the CO2N2, the carbon dioxide nitrogen gas pair. Back in 1991, nobody thought that was an interesting polymer, an interesting gas pair to work with. But of course, by the 2000s, people were getting concerned about global warming, and people were interested in carbon dioxide capture. And if we're talking about carbon dioxide capture from flue gases, then the carbon dioxide nitrogen is a key gas pair to think about. So in 2008, Robeson introduced the CO2N2 gas pair, along with redefining the upper bounds for other important gas pairs, such as CO2CH4, O2N2, and others. Now, being chemists, and particularly Neil, so what Neil loves doing is thinking up new ways of making things and new things to make, and he's really good at it. And of course, if we're thinking about gas separation membranes, then a class of polymers which has been very important in terms of pushing the boundaries is the polyimides. I mentioned that when I was in BP in the 1980s, there was a large group of people working on polyimides for gas separations. And so we were keen to know whether one could combine the idea of a polyimide with a PIM. Now, the thing about a polyimide, of course, is that necessarily there's a single bond at the imide linkage. And so that introduces flexibility. And the whole point of a PIM is that we're trying to take away that freedom of rotation in the backbone. But if we have sufficiently bulky groups near to that to restrict rotation about that bond, then we can have something which is sufficiently constrained that it actually starts to behave like a polyimide. So in 2008, we published the first of a number of papers on PIM polyimides. You might notice that the first name on that is Badaganem. Badaganem was a PhD student when we were first at Manchester, when we were first developing PIMs. So he was on the original patent. He moved with Neil to Cardiff when Neil moved to Cardiff, and later, of course, he moved to KAUST, and we'll see an example of that a bit later. So he's been involved, he's another person who's been involved with PIMs right from the very start. Now, I mentioned we put in a GB patent application in 2003. It takes quite a while sometimes to get a patent through the system. But in the case of the US Patent Office, Neil and I actually had to go to the patent examiners in Virginia to persuade them that we really had a case for a patent, but eventually they accepted it, and in 2010 a US patent was granted, and that was actually followed by another continuation patent shortly afterwards. In the meantime, it's worth mentioning again that the range of pins was developing, and Neil, who loves thinking up new and interesting ways of making polymers, he went back to some really old chemistry, Trogus base formation, and demonstrated that you could use that to make a whole new class of PIMs, the Trogus base PIMs. We've got an example here, which is the PIM EA TB PIM, and again, that's a whole family now of new polymers based around Trogus base polymerization. When we get to 2014, finally we had a European patent granted, and that's also when the first commercial product involving a PIM became available. And that was 3M. 3M licensed the PIM technology from Manchester, and 3M developed masks and things for personal protection in industrial and other contexts. And this particular mask is for people working in an environment where there are organic vapors. And so the cartridges here contain activated carbon to absorb the vapors. And these particular ones have on the side a little sensor where, as that cartridge is used up, a little red bar moves across a window. And the PIM1, is actually at the heart of that sensor. And it's the ability of the PIM to absorb vapors in much the same way as an activated carbon, which is important there. And the design of the sensor enables that to be visualized actually as an interference color when a vapor gets past the cartridge and into the PIM. Unfortunately, that isn't on the market anymore for reasons which are nothing to do with the polymer or the technology. But it was on the market for quite a few years as an example of how a PIM can actually be used in real life. In the meantime, as well as Neil and myself, by 2015, there were quite a few groups working on PIMs and developing new PIMs. In particular, of course, Ingo Pinau's group at KAUST, and Bader Ghanem, who was involved as a student in the very early days with us at PIMS, is by then working with Ingo in KAUST. And in 2015, they felt it was time to revise the upper bounds again, based around a number of new PIMs, particularly tryptophan-containing PIMs. And so they proposed some new upper bounds for air and hydrogen separations. At that point, they didn't particularly suggest any new upper bounds for separations involving carbon dioxide. But that came along a bit later in 2019. And this is a group of people. This was Neil up in Edinburgh now, developing benzotryptophan-based PIMs, and working with John Janssen and colleagues at ITM-CNR in Italy. John Janssen and colleagues in Italy have been another very wonderful set of collaborators over the years. We've done a lot of excellent work with them, and Neil has too, and we're very grateful for all of their contributions over the years. So 2019, they proposed some new upper bounds for carbon dioxide separations, based actually on a few PIMs, but on following the aging behavior to get different points on the plot. When we get to 2022, now, one thing about PIMs, of course, is you do need to be a chemist to make them, well, or at least a reasonably competent in the lab. In 2022, some PIMs were made available through Merck, Sigma Aldrich. Some of these were actually made in Edinburgh and some were made in Manchester. There's a big markup, so they do come incredibly expensive for what they are, but they have been available, and there will be more. They may have run out of their original supply, but there will be more. They should have more PIM1 soon, if not already. So what I've done is to take you through a little bit of a timeline of the development of PIMs and some of the key events. There are a lot of more that we could have mentioned, But what I'd like to do with the rest of the time is to try to bring you up to date with the things that we're still thinking about, still concerned about in terms of research, and it just mentioned some of the recent papers out of very many that have appeared on the subject. But first of all, what are the problems? 21 years since we first published on a membrane application, there isn't yet a commercial membrane application. We've come close. Some years ago, we were working with a company developing PIM hollow fibers for gas separations. Unfortunately, that company became a victim of the 2008 recession, which was nothing to do with our polymer, but we were a victim of it. So we are still looking to see PIMs actually out there with more commercial applications, but particularly in the membrane field, some of the questions that people still have, some of the things that we're still trying to understand and improve on. And one of the things is a fundamental problem with glassy polymers. When we think about gas separations, the field is dominated by glassy polymers, but a glass is non-equilibrium. A glass is a polymer which is trapped kinetically in a certain state. And it can't move easily, but over a long period of time, there's just enough wiggle room that thermodynamics will do what thermodynamics does, which is, we're trying to build space into a polymer, and thermodynamics will always try to squeeze that space out if it possibly can. So that space is internal surface, it costs energy. Thermodynamics wants to get rid of that. And so by one process or another, over time, glasses do tend to very slowly relax into a slightly more dense state. And in terms of permeation behavior, that leads to a decrease in permeability, often with an increase in selectivity, but it's a change. And chemical engineers don't like materials that change over time. So that's something that we probably can't get rid of entirely, because the glassy polymers aren't equilibrium. But it is something we can try to control, and I'll talk a bit about that. And the other thing which we need to be aware of is that glassy polymers may undergo plasticization, and in gas separation it leads to an increase in permeability, often with loss of selectivity as pressure increases. And this is particularly important when we're dealing with strongly interacting gases such as carbon dioxide. So physical aging and plasticization are two things that need to be understood and controlled. And the other thing to be aware of is, of course, a lot of the studies in university laboratories of what are called membranes are actually studies of relatively thick films, where we're talking about thicknesses of 40 to 100 or more microns. And the reason people look at those thick films is because we can make that of a single material. The idea is you get the properties of the material, the permeabilities and such like, without the complications of other things present. But of course, if we're talking about a commercial membrane, then you always want your active layer to be as thin as possible to increase the permeability, to increase the flux, the amount of stuff that comes through the membrane. And a very, very thin film obviously isn't mechanically strong enough to stand by itself in a pressurized process or anything like that. So it has to be on another, have a substructure to give it mechanical support. And this can be brought about in different ways. It could be an integrally skinned membrane formed by processing a single polymer, or it can be a thin film composite structure where the thin layer of the material is going to form and the active layer is supported by a much more porous substrate. And in theory, if we understand the properties from the thick film, that ought to translate into the properties of a thin film. But in practice, it's not that simple, particularly when we're dealing with a polymer which gets its properties by the way the polymer molecules interact with each other, by the constraints on conformational flexibility, because they're inevitably at a surface, things are different to in the bulk. And as a film gets thinner and thinner, you have more surface, less bulk, and the reality that means the properties change. So a thin film isn't the same as a thick film. And in terms of the things that concern us, physical aging is actually much faster in a thin film. That can be a good thing. It means you can get to a sort of a state sometimes that you want relatively quickly, but it can be a bad thing, particularly if the aging behavior is very bad, and sometimes it can be. And also plasticization can be much more pronounced and occur at lower pressures in a thin film than in a thick film. And when we're dealing with high free volume glassy polymers where we try to squeeze in lots of extra space, then in a thin film, we can see very rapid physical aging and very pronounced plasticization. So these are all things that need to be thought about and understood, and this is all part of ongoing research. So just to mention some of the things that we and collaborators have published recently. One of our recent collaborations has been with Colin Scholes and Sandra Kentish at the University of Melbourne in Australia. And we've had a dual award PhD student, Ming Yu. He's just finished now, and he's on a scheme where he gets 2 PhDs at the end of it. So he's got one from Manchester and one from Melbourne. But one thing that he did was to actually review all of the work that has been carried out on PIM1 based thin film composite membranes, and think about many of the factors in terms of the polymer, the processing, the support, which can be very important, and such like, which will affect the performance of TFC membranes. That review is out this year in Journal of Membrane Science. Membrane technology is interdisciplinary. So although I'm based in the Department of Chemistry, I work very closely with colleagues in chemical engineering at Manchester and in people with chemical engineers and people from other disciplines in other places. And a collaboration involving chemical engineering at Manchester and also at the University of Zaragoza in Spain, where we have a very effective collaboration, has been looking at gutter layers for thin film composite membranes. Now, a lot of our research we try to do without a gutter or intermediate layer, just focus on an active layer and a support. But in practice, sometimes an intermediate layer could be really helpful for enhancing permeance and also affecting what happens when you actually coat a membrane in terms of avoiding penetration into the support, which can change the properties of what happens. And in this particular work, which has been published again in Journal of Membrane Science this year, we were looking at graphene oxide as a basis for a gutter layer. When we think about gas separations, a lot of the research we do focuses on flat sheet membranes because they're easy to make and handle and work within a laboratory. But most commercial gas separation membranes are actually hollow fiber membranes. And so another very good collaboration has been with the University of Cantabria in Spain, and they've been developing thin film composite hollow fiber membranes and looking at their performance. Again, a paper come out this year in separation and purification technology. Now, if we think about how to control aging, one approach is to add fillers. And this was highlighted quite a few years ago by Matthew Hill and colleagues, where they took a porous aromatic framework, which interacted in a particularly effective way with PIM1. And this paper in Angewandte Chemie, it's called Ending Aging in Superglassy Polymer Membranes. Ending aging might have been a slight exaggeration, but certainly it demonstrated the possibility to substantially reduce aging effects with an appropriate filler. And there's been a lot of work on mixed matrix membranes where fillers of one sort or another are added to polymers such as PIMs. I shall just mention a couple of recent papers out of many. One of the things when one starts mixing things is getting, particularly with polymers, is getting good compatibility. And so one thing we have been looking at, where we've been looking at metal organic frameworks. These are very popular now to look at as fillers in membranes, in mixed matrix membranes. looking at different ways of combining MOFs with PIMs. And of course, how you go about trying to improve that compatibility can be very important in terms of the properties. And another one, again, from collaboration with the University of Zaragoza, looking at zeolitic frameworks, which again have been modified to try to improve the compatibility with the polymer. So in general with mixed matrix membranes, you usually need to do something to get the interactions right between the polymer and the filler. It's not as simple as just taking two things and mixing them. One thing I should mention is, you know, at the end of the day, my group, we work in laboratories, we carry out experiments in laboratories, but there's a lot to be learned from computer simulations. And over the years, we've had a lot of good collaborators with some people who really know what they're doing with computers. And just to mention some recent work, again, in chemical engineering at Manchester, which has been looking at this whole issue of interfacial defects in mixed matrix membrane, and in this case, looking at the influence of the morphology of the defect on the gas transport through a membrane. Now, one thing about mixed matrix membranes is, again, most of the studies in the literature are on relatively thick films. And in reality, if you want to apply these things, you want to get to a very thin active layer. And so if you're going to have a thin layer, you also need a very small filler. So you have to think about controlling the particle size of the filler and get that down, ideally, to nanoscale. And so here's a bit of work from last year, again involving people in chemical engineering at Manchester and at the University of Zaragoza, focused on thin film nanocomposite membranes. And in this case, again, we're playing around with what we can do with a filler. It was a MOF, but in this case, the MOF was formed a composite with a carboxylated version of PIM1. And so there are lots of things we can do by combining polymers and other things in the right way to obtain membranes with interesting properties. And one of the things we're looking at, the reduced membrane aging. However, when we're talking about inorganic or metal organic fillers of any sort, and some of these clever things we can do in the lab, there's always a question over how practical it will be to scale that up for large-scale membrane fabrication. And so we've been focusing recently perhaps more on what we can do with polymer blends, which might be easier to scale up for fabrication. And for example, if we get the right polymer, I'll say a bit more about that in a moment, we can create blends of things which are similar polymers, but which can have a big effect on performance. And again, in this case, looking at aging performance. Now, as well as adding things, if we have a polymer like PIM1 as a good example, we have some nitrile groups on the backbone, and you can do chemistry on that. You can create all sorts of different functionalities. And this means that if you start with a base polymer, you can create actually a whole range of polymers that would be suitable for different types of separation or different circumstances. You can tailor the polymer for a particular separation through chemical modification. Sometimes you can modify the polymer and then process it into a membrane. Sometimes after modification, it's not processable, but it's possible to do the modification on a preformed membrane. I'm only going to mention one briefly, which is an amine modification, which is always interesting because of its ability to act with carbon dioxide. And it's something we've been looking at over quite a few years, again, in collaboration with John Jansen and colleagues at ITM-CNR in Italy. And recently, they published, it's online as an accepted article in Journal of Materials Chemistry, an attempt to really understand what's going on when carbon dioxide interacts with this sort of polymer. And there's strong evidence that there's an element of chemisorption as well as physisorption going on, which actually leads to some quite interesting behavior and improved selectivity when one's looking at mixed gases as compared to single gases. So we're getting towards the end of my time. So quickly, I'll mention something which has been very interesting to us recently, which is, particularly as chemists, making sure that you start out with the best polymer. So if you're going to add something to it or blend it with something or whatever you're going to do, start out with the best polymer that you possibly can. And that sometimes means going right back to how you polymerize the polymer and what goes on in the polymerization. Because we might draw a structure as though it's a linear polymer, an idealized structure, whereas the reality of what comes out of your polymerization may be rather more complex mixture of different typologies, of different topologies. We may have cyclic, we generally have quite a lot of cyclic, particularly in low molecular weight. We have tadpole structures, branch structures, network structures. And the distribution of topologies for what is nominally the same chemical structure may have a profound influence on permeation properties. And if we think about PIM1, where we're trying to create two bonds at once to create that fused ring structure, if in the early stages of the polymerization, the temperature is a little lower, so things go a bit slower, you're more likely to get monosubstitution, which can lead to a defect, which then further reaction gives a branch. And so just slight changes in the polymerization conditions can actually lead to a quite different product because you can get branch structures. And we can tell when you have branch structures in the NMR spectrum, in that you can actually see little peaks which we associate with those defect or branch points and quantify them reasonably through Lorentz peak fitting. And if we get this branch with this sort of structure, that can actually go on to react further if you push the polymerization longer, creating a four-way linkage. And the consequence of that is that, again, if you push the polymerization for longer, you can start to build up network structures of different types, all of which have an impact on the permeation properties. Now, recently, Andrew Foster, who's been working at Manchester, has gone through all the literature that and all the results we have on thin film composite membranes based on PIM1 to get as much information as possible about the topology of the polymers that were used. Sometimes people didn't realize what they were using at the time, and its effect on the performance. And we see big differences in the performance and the aging behavior depending on the topology of the polymer. Okay, running out of time, very quickly mention that I've talked a lot about gas separations, but there are a lot of other potential applications in membranes and other areas for PIMs. I'll mention one bit of recent work that's involved chemical engineers at Manchester, which is actually focused on proton exchange membranes for fuel cells based on which involve PIMs as well as other things. And I'll also mention the importance of trying to improve the sustainability of the synthesis of polymers for membranes and also think about the fabrication of membranes. Membranes are often promoted as being useful for a sustainable future, which they are, because they're potentially much more energy efficient than thermal separation methods and other separation methods. But we also have to think about how we make the materials that are used and how we make the membranes. And that's where, and this is something that George has been very keen on developing, that's where there's still a lot of scope for developing new ideas and new ways of doing things. And actually something that George started quite a while ago when he was at Manchester was a potential green solvent as an alternative to Polar Clean. Alicia Ayaz, who I am heading towards retirement. Alicia will be my last PhD student. But she's been looking at that solvent in PIM synthesis, and we've had a recent paper out on that. But I think I'm running out of time. I should say research doesn't happen without money, and a lot of that, we've had a number of sources of funding over the years, but a lot has come from the Engineering and Physical Sciences Research Council. And currently we're involved in a collaboration, a program grant known as SynHiCell, which involves 6 universities in the UK involved in membrane research. And of course, an enormous number of people over the years have been involved in our work on PIMS. So at Manchester, we've had a lot of students and postdocs in chemistry and chemical engineering contributing to work on PIMS. I've already mentioned a lot of collaborators. There is not space on one slide to mention everybody, unfortunately. We're grateful to everyone, but I do want to mention in particular people at Zaragoza, Cantabria, ITM-CNR and Melbourne who've been involved in some of the recent papers that I've mentioned in the latter part of the talk. But I think I need to say now, thank you for listening, and are there any questions?
Thank you, Peter. Thank you for the nice summary of the PIM field and your role in it. So let's check if there are any questions from the audience. Please use the chat to write your questions, which I will read. Okay, let's give the audience some time to type their questions. In the meantime, so you summarized 21 years of PIMS, right? Referring to the past. But what about the future? Can you predict what will be the next 21 years about?
I hope that we're going to see more real applications of PIMS. And I think we are, because there are lots of things, lots of potential applications. I think now that our patents have expired or expiring, you're going to see a lot of things happening. We won't get anything out of it, but it will be good to see things in place. I indicated that we've had some close calls. It's a surprisingly frustrating business sometimes trying to get things into real application. We've had one application, but then after a few years that was dropped by the company for reasons which were actually nothing to do with the technology. It was a change in the supply of one of the components. We were quite advanced in working with a membrane company, which then folded again as a result of the 2008 recession. We were actually very far advanced in negotiating a license with a company on another sensor application when the company completely changed direction and dropped the entire area that we were working with. Those sorts of things happen in this world, but I'm looking forward to seeing more applications. And I'm actually excited that there are a lot of young people now building on what we've done. And I'm pretty sure that some of them have some bright ideas that I wouldn't even have dreamt of that are going to take PIMS work forwards into the future.
Okay, so one of the focus areas should be more applications for PIMS. And what are the pressing challenges to solve in terms of chemistry, new polymers? What is the direction there?
So a lot of my work is, there have been a lot of new PIMS, and Neil has been wonderful, and Ingo has been wonderful at developing new PIMS. We've done a lot of work on the old PIM1, partly because, although they're not cheap, the two monomers are readily available and actually could be made much more cheaply if someone decided to scale up. And because it's got enormous scope for modification in various ways. I think what I've mentioned at the end about topology control is really, really important. And I think that's going to become important. People are going to realize how important it is in other areas as well. But it does mean learning how to control the polymerization in a way that you really get what you want. And with a step growth polymerization, that's always tricky because very small changes in the conditions can change the outcome. So there's work to be done on finding the best way of making these things. I actually suspect what we're going to find is that what we've learned about how to develop a PIM-type structure will ultimately be used not necessarily in making a polymer and processing it conventionally, but actually in new ways of making polymers, in situ polymerization to create the right membrane structure, for example. That's something we've started to work on, but I think there's a lot more scope by looking at that.
Okay, and regarding the topology, so you presented various different structures, right, that you can obtain during the synthesis of PIMS. But then how do you control this? If, let's say, you know that one particular structure is better suited for an application, then can you fine-tune the polymerization process to obtain one single topology?
I'm not sure about one single topology, because as in polymer science with molar mass, you never get well, unless you're making a dendrimer, you never get a single molar mass. But you can narrow the distribution. You can, it's we're talking about distribution in the same sort of way. But what you can do is you can get something which, on average, if you like, is the sort of thing we're looking. It is about, in particular, control of temperature in the early stages of polymerization is critical. And actually, company. This is true for other polymerizations as well, and there are ways of doing that. It's not pushing it too far. It's actually understanding and monitoring what you're doing. So we do tend to monitor temperature and torque on the stirrer as we go. So as with some other commercial processes, it's a combination of knowing what you're aiming for, but also you actually have to monitor the reaction to make sure that it's doing what you want it to be doing. But it is potentially achievable. So,
okay, so there's a lot of know-how to learn.
There is know-how. There is know-how.
Okay, I'm looking at the chat, but we don't have any question at the moment. So then maybe I can ask you one more question. So PIM1, so that's the original PIM that you reported, PIM1. And since then, you presented a lot of new structures, and in the literature, there are tons of different PIMs being synthesized. But it seems that still PIM1 is the main hit here, which has a relatively easy synthesis, good processability, high surface area. So it seems like that the very first one that you managed to synthesize has all the good properties, and it's very difficult to beat it. What are your thoughts on that? Is it true, or?
I guess, well, it was. I mean, our first paper actually involved a number of PIMs, and in the early days we looked at a lot of structures, but an awful lot of the PIMs do involve a lot of work making the monomer. So it is an advantage of having two things that you can just buy in. We actually, I suspect a lot of researchers know this. You do something, you think that's going to be the beginning, and then you struggle to beat it. And it was quite a while. We were making quite a few PIMs. It's quite a while before we could say this is actually better than PIM1 in some way. And it can be quite frustrating for PhD students who spend a lot of time to make something, and its properties are just a little bit worse than PIM1. But actually, they might have advantages, and we're learning all the time. But it was a little bit unfortunate, if you like, that we stumbled across PIM1 first.
Yeah, that's very interesting, actually. Okay, in the meantime, we have a question. A nice overview on PIM evolution from birth to now. If the molecular spacer is more bulky, is there some indication that polymer will be more imperfectly pegged and hence more selective? Can you see the question, Peter?
Yeah. Sorry, I didn't quite catch the beginning of the question. I'm not sure.
Yeah, if you go to the chat, you can see the question there.
Chat. I'm trying to. Hang on, I'm looking around to find the chat button on this system. Oh, private chat, there we go. Oh, hang on, I think I have to go to chat. Ah, yes, find it. If the molecular spacer is more bulky, I think it all depends on. Very often, if you have something that's bulky, all that does is fill the free volume to actually lose free volume. So it's about the nature of the bulk. But we've talked about imperfect packing. The other concept to think about is it's sort of internal free volume, where you have so the tryptine structure is particularly good because you've got a little sort of pocket that it's very hard for something else to get into. So I don't think it's as simple as more bulky. It's a question of the right sort of bulkiness. I think that's the answer there.
Okay, we have another question.
Can apply PIN membranes for especially membrane distillation? Yes, there are people looking at PIN-based membranes for membrane distillation, so I do believe so. And there has been some work on desalination membranes, not by us, but if you go into the literature, there is some. I mean, we've tended not to focus on desalination, or at least certainly not reverse osmosis, because, to be honest, RO membranes are pretty much as good as you can expect them to get. Well, we have looked at other types of desalination, including electrodialysis and such like, and there are people looking at membrane distillation, amongst other things. There's 1 or 2 papers on that in the literature if you look.
All right, thank you, Peter. Okay, I think we have no more questions through the chat. So, Peter, thank you very much for the podcast and the webinar, and taking us through the past 21 years of PIMS and giving an overview of, or a glimpse of, the future of PIMS. Thank you very much. And I suppose if anyone has any other questions, then we can reach out to you via email.
Absolutely.
So thank you on behalf of the EMS for accepting our invitation to give this talk today.
Thank you very much. It's been a pleasure.
Thank you, Peter. My pleasure. Take care.
Bye.
Bye.